Alright, today we're going to be talking about this idea of orthogonality. So, up until this point we've talked about how nice it would be to diagonalize a matrix. And we're not always going to get this property, but there's still going to be some things that we could do that will be useful for us to represent the matrix in a different way using something called an orthogonal basis. But you might see this in applications in future classes. So what we're going to try to do today is we're going to try to make sure we understand what it means to be an orthogonal vector, how we could find a set of orthogonal vectors, and then give a little bit of a sense of what an orthogonal matrix would be. So let's talk about orthogonal vectors. So before we discuss some of our least squares sports ranking stuff with the Massey method, we had two terms that we used. We're going to need to kind of remember these for what we're doing today. So the first term is that of the inner product or the dot product. So the inner product or dot product between two vectors, u and v, denoted u dot v, is basically equal to the sum of the products of the entries. So if you've got two vectors that have the same length, so notice they're both in Rn, then you'll take their first entries and multiply them together, and add their second entries multiplied together, and then add their third entries multiplied together, all the way until you get to the last entry. The other concept we're going to need from before is the idea of the length or norm of a vector. And so this length of a vector is denoted as being the square root of the sum of the squared entries of the vector. Or another way to think about it would be the square root of the dot product of a vector with itself. All right, so we also have a couple of other definitions that we'd like to think about. The first is the definition of orthogonal. Two vectors u and v are going to be considered to be orthogonal if u dot v equals 0. We'll often think of this as being perpendicular vectors. In case you're wondering where that idea comes from. The other definition we're going to start off with here is given a set of vectors u1 through um, we say that it is an orthogonal set if ui dotted with uj is equal to 0 for every I and j in the set. Here where I is not equal to j. So basically u1 should be orthogonal to every other vector. u2 should be orthogonal to u1 and every other vector. u3 should be orthogonal to these vectors and all the other vectors, and so on and so forth. Every vector has to be orthogonal to every other vector to say we have an orthogonal set. So, for example, let's say we wanted to look at this set and show that it was orthogonal. What we would do is we would just check the dot products between each of these vectors pairwise and make sure that all of those dot products were 0. So let's take u1 dotted with u2. So that should be negative 2 times 1 plus 1 times negative 1 plus negative 1 times 3, which will give us negative 2 minus 1 plus 3, and that is 0. If we take u2 and u3 and dot them together, what we'll get is we'll have 1 times 4 plus negative 1 times 7 plus negative 3 times negative 1. So that'll be negative 4, or sorry, that should be a positive 4. I don't know why I've got a typo there. It should be positive 4 minus 7 plus 3, and that'll give us 0. And then we also want to go ahead and take the inner product of these two and show that it's 0. So we'll have negative 2 times 4, which is negative 8. We'll have 1 times 7. Don't know why I have a negative 7 there. This little bit is full of typos. I apologize for that. And negative 1 times negative 1, which will give us a positive 1. So negative 8 plus 7 plus 1 will be equal to 0. If we go ahead and add another vector here, 0, 2, 2, and put it with our set, we want to know if it still would end up being an orthogonal set. So we'd have to go ahead and check the dot product of this vector with every other vector we already had. So if these are u1, u2, and u3, The dot products will be u1 dotted with v, so that would be negative 2 times 0 plus 1 times 2 plus negative 1 times 2, so it would be 0 plus 2 minus 2 equals 0. Okay, so it's orthogonal with the first vector. Then when we go to check the second vector, u2, we'll have 1 times 0 plus 2 times negative 1 plus 2 times negative 3. So that'll give us 0 minus 2 minus 6, but that's going to be negative 8, which is not 0. So since this inner product, this dot product, is not 0, we know that this set where we just add this vector onto it is not going to be orthogonal because of a single of the inner products not being 0. And so we don't even need to bother checking this last one. We could if we wanted a little bit more practice. So let's do that. If we took u3 dotted with the vector, we will have 4 times 0 plus 7 times 2 plus negative 1 times 2. So that'll be 0 plus 14 minus 2, which is 12. And so our new vector v is not orthogonal to the third vector either. Okay, so with this being said, I want you to kind of check on your own to see if you're understanding this idea of orthogonal. So we want to know which of these sets of vectors here is not going to be an orthogonal set. Now, I recommend that you actually bear these out and try all 5 of them, because you want to be able to check if a set of vectors is orthogonal. But also because the one that you might jump to because it looks the scariest might actually work out pretty well. So take a moment, pause the video, and try to see if you can figure out which of these is not orthogonal. Alright, I have no way of knowing if you've paused the video or not, so I'm just going to keep going. So if we take this dot product, we'll get 1 times 1 plus 1 times 0 plus 1 times negative 1, which will be 1 plus 0 minus 1, which will be 0. So this is going to be orthogonal. So we don't want those. Next we'll check if this is orthogonal. So we'll get 2 times negative 6 plus 3 times 4, which will be negative 12 plus 12, which will be 0. So that's not going to be our non-orthogonal set. So if we look at this set, we'll get 3 times 0 plus 0 times 1 plus 0 times 0 plus 2 times 1. So that's 0 plus 0 plus 0 plus 2, which is 2, which importantly is not going to be equal to 0. So C is going to end up being our set that is not orthogonal. Now just for extra practice, I'm going to go ahead and show the other 2 as well. So if we want to show this is orthogonal, we'll take 0 times negative 1 plus 2 times 0 plus 0 times 3. And we'll get 0 plus 0 plus 0, which of course is 0. So that one won't work out. And then this last one's probably the most difficult to see immediately, but notice we're taking the cosine times the sine plus the sine times the negative cosine. So because these are being multiplied, we can go ahead and reorder them. So that's sine of theta times the cosine of theta minus the sine of theta times the cosine of theta. Well, those are the same thing, just opposite signs. So that's going to be equal to 0 for us as well. So that's great. That is really nifty. So we've got a bunch of sets here that are orthogonal, but we do have the one that isn't. All right. So, theorem time. Suppose we've got 2 vectors, then our dot product between them will be 0. In other words, they will be orthogonal if and only if the length of u plus v squared is equal to the length of u squared plus the length of v squared. So this formula might look familiar to some people. And so let me see if I can draw a little bit of a visual here to show what's going on. Essentially what we're saying is that if we've got some vector u here, and we've got some other vector v here, and they're orthogonal to each other, I'm going to draw that little 90-degree thing here, then the length of this side squared plus the length of this side squared will be equal to the length of this side squared, which is u plus v. Hey, look. It's the Pythagorean theorem. Would you look at that? So here's how we're going to prove it. Not actually go through this proof. It's pretty short. If we have two orthogonal vectors, by definition their inner product is 0, then u plus v squared, the length of that squared, will be equal to u squared plus 2u inner product with v plus length of v squared, which of course the length of, or u dotted with v is 0, so this part goes away, and so we're just left with the length of u squared plus the length of v squared. So that's just reading this formulation, and we get the theorem. So that's really nice. So let's try to verify this for these two vectors. So before we've seen in an earlier example that if we take and add these, we get negative 1, 0, 4. So that's just negative 2 plus 1 is negative 1, 1 plus negative 1 is 0, and negative 1 plus negative 3 is negative 4. If we wanted to go ahead and find the length of this, we would go ahead and then square it. We would take the square root normally of negative 1 squared, which will be 1, plus 0 squared, which will be 0, plus negative 4 squared, which will be 16. So 1 plus 0 plus 16 will be 17. So we have the square root of 17 squared, which will be 17. Now we know that if this is going to be u and this is going to be v, that the length of u squared will be negative 2 squared, or just 2 squared, plus 1 squared, plus negative 1 squared, which is the same as 1 squared. And we want to go ahead and take then 4 plus 1 plus 1, which is 6. And we're taking the square root of that, but we're squaring it, so that'll go away. And then we also want to take, for v, because we're squaring these, it doesn't matter if we're doing the positive or negative here. We have 1 squared, which is 1, plus 1 squared, which is 1, plus 3 squared, which is 9. So 1 plus 1 plus 9 is 11, and the square root of that squared is 11. And so we take, if we add these two together, 6 plus 11 equals 17, which did go ahead and work for us. So indeed, we do get that the length of u squared plus the length of v squared is equal to the length of u plus v squared. So note that in general, this doesn't work. This only works when we have two vectors that are orthogonal to each other. And also note that this only is working when we go ahead and square those lengths, because the square root of 6 plus the square root of 11 is not the same as the square root of 17. All right. So we're also going to talk a little bit about orthogonal spaces. So definition time, let V be a vector space. We say that a vector U is orthogonal to V, the whole vector space V, if U dotted with a vector V in that vector space for all the vectors in that vector space equals 0. So how we would show this is we would take a representative vector from V and show that u dot that representative equals 0. And so if we just pick something that was representative and not necessarily something that was a particular vector, and we showed that no matter what the representative was, whatever we picked of those values, we get 0, that would show that that vector was orthogonal to the set of the vector space. Another definition, the set of all vectors u that are orthogonal to V is called the orthogonal complement of V and is denoted by V raised to the, it looks like V raised to the power of the symbol we have for orthogonal. We say this as V perp. This is talking about the vectors that are perpendicular. Note that this V perp set here is going to be a vector space. And so we could check all the different properties that we needed to, that would be associated with that. All right, so say that we've got a basis for a set V. Then we say that a vector u is an element of V perp, that is, u is orthogonal to every vector, if and only if u dotted with each of the basis vectors, we take u, the dot product of u with every single one of these basis vectors is going to be 0 for every basis vector in the basis. And so this isn't much of a formal proof, but the way we can think about this is that if a vector is orthogonal to all of the building blocks, the basis vectors, then it has to be orthogonal to everything you can build or span with those vectors. So we might think, okay, well, V perp's a vector space. So say we have a set V that is the span of some vectors. How would we go ahead and find a basis for that? So the solution would be to go ahead and have these, make sure that this was a linearly independent set first, and we want to find a linearly independent spanning set for the set of all vectors that are orthogonal. We don't want to check all the vectors individually, so instead we're going to find all the vectors u1, u2, u3, u4, because these are length 4, such that when we take the dot product of u with each of those vectors, we get 0 as the output. So essentially we're taking u dotted with v1, which would be u1 times 1 plus u2 times 1 plus u3 times 0 plus u4 times 2. That's just kind of going down the entries here, and we're setting that equal to 0. If we wanted the dot product of u with v2, that would be u1 with times 1 plus u2 times 1 plus u3 times 1 plus u4 times negative 1, which was set equal to 0. And we also want to make sure that this vector dotted with this vector is 0. So we'd take u1 times 2 plus u2 times 0 plus u3 times 1 plus u4 times 1. And so we would get this. And this is just going to give us a system of equations to try to solve for what u might end up looking like. So we want to go ahead and solve this system of equations. Note that this is really just taking A transpose augmented with the 0 vector, where A in this case would be just each of these vectors on their own. So if you took this and you took the transpose, that's what this looks like over here, in case you're trying to figure out the quick and easy way of writing. So solving this system gives us this system of this reduced row echelon form. And as we take a look at this reduced row echelon form, we notice that we have infinitely many solutions. We notice that by our free variable here. So u4 is going to be a free variable. And so we can go ahead and write u1 and u3 in terms of u4. So if we rewrote this, we'd get u1 equals negative 2 times u4. This is just going to say that u2 equals 0. This will say that u3 equals negative 3 times u4. And of course, u4 equals u4. So that means that since we're down to just a single free variable here, we should be the span of just a single vector. And so vperp is the span of negative 2, 0, negative 3, 1. And so that comes from the negative 2, the 0, the negative 3, and then 1. So since it's spanned by just a single vector, it's going to automatically be linearly independent, and because of that, it's going to be a base. Okay, great. So say we wanted to go ahead and write, find a basis for a different set here. So say we had the span of this set, and we want to find the basis for vperp. We could solve this by setting up the augmented matrix where we have each of these vectors as rows instead. So we could go through the same process we did on the previous page, where we took u dotted with v1 equals 0, u dotted with v2 equals 0, and u dotted with v3 equals 0. And that's how we get this matrix, by taking these dot products and setting them equal to 0. Given the reduced row echelon form here, gives us a solution of all zeros, which tells us then that the perpendicular, the vperp, is just going to be the 0 vector. So that means the only vector that's orthogonal all of them is the 0 vector. Alright, so that then gets us into the idea of wanting to have an orthogonal basis. So having this orthogonal property can be very useful for us, so we want to know how we could get a basis of it. So theorem 14.3, a set of non-zero orthogonal vectors is a linearly independent set of vectors. So this is really good to know. If we've got a set of orthogonal vectors, then that set of vectors is going to be linearly independent right away. So that's really nice for us, as long as they're also non-zero. So if they're orthogonal, we get the linear independence immediately. So that's kind of nice for us. We have this little proof here that kind of talks about it, but we're going to skip that for now. You can read it if you so choose. Definition 14.7: a basis is made up of orthogonal vectors is called an orthogonal basis. So why is this basis useful? Well, first of all, we just talked about how orthogonal sets are automatically linearly independent. The other thing is that they are going to be very stable for us. So we'll briefly mention the idea of stability a little bit later. And so definition time: a set of vectors is orthonormal if the set is orthogonal and also the length of each vector equals 1 for all the vectors that you have in your set. So by adding this normal part here, making them orthonormal, that is what goes ahead and gives you something that is different than being orthogonal. You want to also have the length of 1. So how do we go ahead and normalize? Well, what we do is, once we get an orthogonal set, we can go ahead and normalize the vectors by dividing each vector by its norm. So in other words, we would make u1 equal v1 divided by its own length. The second vector would be the second vector divided by its own length, and so on and so forth, until all of our vectors were normalized. We also have another theorem that says, suppose we have an orthogonal basis, then any vector can be written as u equals a1 v1 plus a2 v2 plus n vn, all the way summed up through there, where a would be equal to v1 or v sub I dotted with u divided by the length of v squared. So in other words, by having an orthogonal basis, we can go ahead and be given what the coefficients will be for any vector that we'd like. So that's really nice for us. It means that we have a very quick way of finding those coefficients if we know we're dealing with an orthogonal basis. There's a little bit of a proof of why we get those coefficients so easily. All right. So given a subspace V subset of W, V is equal to W plus W perp. In other words, what we're saying is that any vector can be written as V equals W plus W perp, where W is in W and W perp is an element of W perp. So this is a thing that we can we're essentially saying we can go ahead and write any vector in the parent space as a vector from the subspace plus a vector that is from the perpendicular space. We essentially can break it down into things that are orthogonal to this space and things that are in that space. All right, so let's consider this example from before. We want to know how we know it's a basis for R3. So in example 14.1, a couple of pages ago, on the first page actually, we showed here that this set was orthogonal. And we now have a theorem that says that when you have orthogonal vectors, they have to be linearly independent. Now, since we know that R3 is three-dimensional, we know that since these are linearly independent, they form a vector space of dimension 3. So that means they'll give us a basis for R3. All right, now let's say we wanted to go ahead and write a vector as a linear combination of this basis. So say we wanted to go ahead and figure out how we combine these three vectors to get this vector. Well, one way to do it is to solve the system of equations, right? We could go ahead and we would take -2, 1, -1, 1, -1, 3, -3, and 4, 7, -1, and augment it with 3, -1, 5, and then get the reduced row echelon form. That's one way to do this. But we now have another theorem that allows us to go ahead and get this a different way. And this different way is often going to be less prone to error. So what is this way? Well, we go ahead and use our theorem to take and make this coefficient equal to u dotted with the first vector, so the vectors dotted together, divided by the length of the first vector. So just to be clear, this is v1, this is v2, and this is v3 in the notation. We then would find the second coefficient by taking the vector dotted with this vector and dividing by the length. And we could find the third coefficient by going ahead and taking this vector dotted with this vector and dividing by the length squared of this vector. And so that would go ahead and give us a way to find each of those. So if we wanted to find, for example, alpha 1, we're taking u dotted with v1 and then dividing by v1 dotted with itself. So this would be 3 times -2 plus -1 times 1 plus 5 dotted with -1 divided by -2 squared plus 1 squared plus 1 squared. So in the numerator, we get negative 6 minus 1 minus 5. So negative 6 minus 1 minus 5 is negative 12. In the denominator, we get 4 plus 1 plus 1. So that's negative 12 divided by 6, which is going to be negative 2. We also could go ahead and find alpha 2 and alpha 3 in a similar way. So alpha 2 will end up being negative 1, and alpha 3 will end up being 0. And so that means that u will be equal to negative 2 times the first vector plus negative 1 times the second vector plus 0 times the third vector. So that just kind of shows another way that we can use these ideas of having an orthogonal basis in order to find what these coefficients are going to be. In the next video, we're going to end up talking about the idea of projections, and this will help us get a process for finding a basis that is orthogonal. So if we have a basis that's not orthogonal, we can find one that is using this process.